this around. All right. So are we on? All right, so welcome to the class. This is the main page for Canvas. I think almost everybody is on, so I suppose you're not on this page yet. But you should have received an email in your student account to get on this page. And if it's not there, then Kat can work with you to get you on. All right. So for those of you who've had number theory before, this is very much a continuation of number theory. The course is going to be run very similarly. If you didn't take number theory, then I think you'll fall in fairly quickly. There are a lot of people who can help you. I can help you, etc. So let's see. Let's just briefly get people's names, and we can start. I think we can start at the beginning. Should we do the same thing again? Say name, where you're born, your high school, your major, and what you want to do. Yeah, go. Yeah, if they don't remember last time, they'll remember this time. So go ahead.
I'm not going to remember the order.
Okay. Yeah.
Well, hello, everyone. My name is John Suter. I'm a math major. Graduated from Visay, Oklahoma at Visay High School. I want to do data analytics, anything to do with data. And what else?
No, I think that you're a math major, right?
Yes.
Okay. Yeah. So, yeah, I think what came out in the class last time was that a lot of people are interested in data analysis. And as a department, we're definitely moving in that direction. So, and I will certainly keep that in mind when I'm teaching these classes. All right, so go ahead.
Hi, everybody. I'm Christina. I came from Houston, so I graduated from high school there. And I'm a math major, and I would also like to be a data analyst.
Okay, all right, very good.
I'm Jenny Burrow. I was born in Naples, Florida. I went to high school at McNeil near Austin, and I guess in Austin. I am a math major, and I also want to do analytics.
Okay, all right, please.
My name's Irma. I guess I was a math major at UT. I work for a real estate tech company and I negotiate contracts. And I'm taking this class to boost my GPA for grad school.
Okay, do you live here in Killeen or?
No, I live in Austin.
Oh, okay.
Yeah.
Okay, very good, yes.
Hello everyone, I'm Zena. I grew up in Belgium. I ended up here because of the military, so, and I'm a math major.
Uh-huh.
That's it.
You're pre-med, right?
Yes.
Yes. Yeah, you want to be a doctor.
Bless you.
Yeah. Okay. Well, you want to be a specialist or?
Nah, I'm not sure yet.
Okay.
I'll get there first and then I'll
Okay.
figure it out.
Okay. All right. Good. All right, Mike.
Mike Chandler, retired military. Pushing 60, math major, and I'm just hoping to get a math degree before I die.
Okay. Okay. Well, I'll tell you, the other side of 60 is still good. So I think a lot of people, just from hearing where people are from, I think probably a lot of people have some kind of military connection. Is that right? Well, I mean, did you grow up military? No. No, okay, but you could hear people that were born in, it seems like, near installations. But all right, so anyway, once you get on Canvas, you will become familiar with this page. And I made a video introducing the different features. So just to go through, that's the syllabus. This is the textbook that we'll be using. It is online, and you can get a PDF and print out if you want to, or you can buy a print version. The book has a complete set of YouTube videos that you can watch that gives you background for each chapter. And I will be working exercises in class, and I'll be posting them on YouTube. Now, I'll also be posting the class notes on OneNote, and I haven't put that link here yet, but I will after the class. Here's the first assignment. We will be using a software called, what's it called? GradeScope. So now, I see the people here smiling who used it last semester. I think that we'll make it better this time. Kat, you need to, you can actually do that now. You can attach the sheet to this webpage.
She told me how it worked last semester. I thought I got it put it in Gradescope, and I thought they could see it in Gradescope.
No. So you put it on this page. I don't know if you can. It would be best if you attached it to this assignment.
Yeah.
All right. I don't know if you do it here or you go to assignments, but the way Gradescope works is that you print out a PDF form and you write your homework on the form, and then you scan in the form. The form just tells you, do this problem on this page. Now, the reason that you do that is that when the homework is graded, then we can grade one problem at a time. We can click on a problem and grade exactly that problem. So it's much more convenient for our grading. But by the end of class, you'll have that there, and I'll show you what it looks like. But please remember, when you submit your homework, you do need to submit it on this form. You can print it out, and then write it on the form and then submit. Some people use tablets and they just write on the form using their tablet. That's okay too. But the problems have to be in the same form as the submission form. So I'll be returning to that point by the end of class. Yes?
So do I just upload the PDF to this?
Yes.
Or is there something on Gradescope I
No,
export?
just the PDF. Just the PDF. Okay. So as you can see here, we have. Hopefully they can hear. So I need a wireless mic. So you can see that we have a lot of accessory materials for you to understand the content. So there's both the textbook, which has helps in it, and the videos. So what I do is pretty much work exercises during class. I expect you to get the background material from the lectures, from the text, and from the videos. And then during class, I'll work exercises to reinforce those concepts. Now, I already have a couple of videos, and I'm going to kill myself, so I think I better unplug this. I already have a couple of videos which you can access this way. All right, so I did some exercises from sections 7.1, 7.2, and 7.3. I'm starting with a topic called Symmetries. And the reason I'm starting with this topic is the feedback I've gotten is that this is kind of a fun topic and it kind of ramps you up slowly. I'll tell you that my daughter took abstract algebra at UT, and it almost killed her. It almost killed her. Yeah. So this course is quite a bit different. Quite a bit different.
Happy to hear.
Okay. So what I'm going to do is just look at chapter 7 a little bit, and then I'm going to do some problems from section 4. And so I might be going a little bit past your full understanding, but if you go back and watch these videos, I think that will kind of fill in the gaps. But because this is very visual and geometric, I think you can still follow what I'm doing. Right? So let me go ahead and go to section. Whoops. Let me go ahead and go to section to the textbook, which is back here. There's not that. We're done with that. We're done with that. And we're done with that. And we're done with that. Sorry, I didn't get to close all my stuff from my last class. And I think we're done with that. So we're still here. All right, so let's go to the textbook. And we're going to go down to chapter 7. All right, so we start down here. Now, what is a symmetry? I think people have a basic idea of what a symmetry is. You think of an equilateral triangle. That's symmetric. Or this thing is symmetric. Now, what does it mean that it's symmetric? Well, it kind of looks the same different ways. A way to quantify that is notice that if you take this thing, forget about the shading, okay? Just look at the shape. If you take this thing and you rotate it by 120 degrees, it doesn't look any different. If you think if I rotate it by 240 degrees, it still doesn't look any different. Right? So what you're doing is you're doing a motion and you're ending up with the same thing. So something is the same, something is preserved under a motion. That's the basic idea of what symmetry is. Now, what's a motion? A motion is a function. A motion means you're moving one point to another point. We can think of that as a function. So, in particular, when I talk about moving one point, this rotating 120 degrees, that function is a rotation. So, in this chapter, we'll be looking at some particular types of motions, which are rotations, and there's also flips. Imagine a vertical line here, right? And if you flip this about the vertical line, it would still look the same. Right? So we're going to be looking at two different types of motions, rotations and flips, and what they do to different objects. Right? So you can see that I think I can show this here. These are exercises I did in the video, so you can go back and watch those. You can see that many logos have symmetry. And why is that? Because it's eye-catching. Your eye looks at this, and it's just a natural part of people, what people do when they look at images. They say, well, you know, there's something symmetric about it. There's something nice about it. Right? You can see this one, for instance. If I rotate this by an angle, it's going to look the same. If I draw a line here and I flip it, it's going to look the same. Okay. So one thing I mentioned in the videos is if you want to cut out shapes and do this, then it helps you visualize. You can do that. So it's a very visual topic. Okay, so that's just some examples of symmetries. Okay. So just briefly go over 7.1. So when I say flips, it's also called reflection. Okay, you can think of putting a mirror there. If I took this logo here and I put a mirror, if I put a mirror right here and looked in the mirror, I put a vertical mirror here and I looked in the mirror, and it would look like the same thing. So that's why you call it reflection. Or I could hold up a mirror to that, and it would look exactly the same. Okay. All right. So, so this reinforces the idea that a rotation is a function. When we talk about, we're going to talk specifically about geometrical regular polygons, because regular polygons are very symmetric. And you can see in this case you have a hexagon. Just think of a stop sign. I'm going to identify the hexagon by its 6 vertices. Okay, because where the vertices go determines also where the lines go. Now if I think of a 60-degree rotation, that takes this point to this point, it takes this point to this point, this point to this point, and so on. Okay, so it's a function. A goes to B, B goes to C, C goes to D, and so on. And you can see how that's represented down here. One way to represent functions is by a set of ordered pairs. So so I'm saying what this says is a 60-degree rotation is a function. It maps A to B, B to C, C to D, D to E, E to E, E to F, and F to A. Now, if you're a little bit rusty on functions, there is a chapter back here on functions. Chapter 5. He's skipping around for me. And two important concepts of functions are one-to-one functions and onto functions. If you don't remember that, you can go back and look at those sections. A one-to-one function means that functions have inputs and outputs. A function takes an input into an output. One-to-one function, for each output, there's at most one input. An onto function says for each output there's at least one input. So if it's 1 to 1 and onto, then each output has exactly one input. And again, I go more into detail about that in the video. So we have these functions. All right. You can see in this exercise, I'm asking. Well, all right, we can talk about this. I think I talked about this one in the video. If you think of a hexagon and you rotate it 60 degrees, and that's represented by this function here, by the set of pairs. So my question is this function 1 to 1?
Yes.
So look at each output. Look at each output. The second one in each pair is the output. The first one in each pair is the input. All right. So what are the outputs here? This one has output B, C, D, E, F, and A. So does each output have a different input?
Yes.
And the answer is yes. Because you don't see a D listed twice. Right? You don't have CD and AD, you only have listed once. So this function is 1 to 1. Now is it onto? Now how do you tell onto? Onto means that you look at the list of possible outputs and see if each one is represented. Right? The possible outputs are A, B, C, D, E, F. Are they all represented here?
Yes.
Yes. A is here, B is here, C is here, D is here, E is here, F is here. So all the outputs are represented. This function is 1 to 1 and onto. A function that's 1 to 1 and onto is called a bijection. And one of the things that we talk about are symmetries are bijections. And if you think about it, it makes sense. Because a symmetry takes the object to itself. If it takes the object to itself, it has to take it to all of itself. So it has to map to everything, and it has to take it to itself, each point to one point. So if you think about it, it makes sense that a symmetry should be a bijection.
Are all symmetries bijections?
Yes. Yes. Well, you can try to think of one that wouldn't be. All right. All right. So when we represent symmetries, we're using the corners of the geometrical object to identify the position of the object. So rather than talking about the lines, I'm just talking about the corners. So here's a representation of several symmetries. So I labeled it the corners of this rectangle A, B, C, D. Typically, we do label the corners in counterclockwise order. It's not necessary, but it's probably better if you do that because that's the consistent way we do it in the chapter. So you can see that here I'm talking about different motions, different possible motions of the rectangle. Right, here's the original position of the rectangle. That's the final position of the rectangle. What happened to the rectangle? Nothing. Okay, it didn't move anywhere. That's called the identity. Okay. All right, now here's another one. Here it says if you do 180-degree rotation, you take this thing and you rotate it 180 degrees, then if you think about it, that's where the corners end up. Okay. So, now be a little bit careful here. In this motion here, I would have to say that A ended up in the position where C was at the beginning. So I would say that this motion maps A to C. This motion maps B. Where did it end up? It ended up over there. That's the position where D was originally. So this one maps B to D. This maps C to the position where A was originally. And again, I talk about that in the video that I did already. So you will be having to look at pictures like this and figure out how would I write this motion as a set of ordered pairs. Right. Now let's move on. Okay. Now one thing that you can do with symmetries is compose them. What does compose mean? It means you do one symmetry and follow it by another symmetry. You can do that with functions. I can take f of x and then I can take g of f of x. Right? I could take f of x equals x plus 1, and then I could take g of x equals x squared. So if I took g of f of x, I take x plus 1 and then squared. Or you can compose functions. So you can think about that. I can rotate something and then flip it. Is that still a symmetry? And the answer is yes. When I take the hexagon and rotate it, it doesn't look any different. If I flip it, it still looks like a hexagon. It's still a symmetry. So this is a very important property of symmetries, that you can compose them. Okay. So here they have some exercises talking about just doing this for some particular symmetries. Now, let's see. What is this talking about here? If you remember, so let me just snip this. Go to my OneNote, and then here I'll just say symmetries in class. And today is what? Today is 118. Okay. And let me. Okay. All right. So what's this talking about?
The rotation.
Yeah, this R180. Where's my tablet? This 180 here. I want to. Can I get rid of that? I just want to get rid of that. Go away. Stop. I don't want the buttons. Because I'm left-handed, so it gets. It's okay. The 180 means 180-degree rotation. Okay. Now this is this is referring to a rectangle. Let's just write over here. Okay. So I'm starting, this is, here I have, I can do it like before, A, B, C, D. So what does this notation mean? This means that A goes to C, B goes to D, C goes to A, D goes to B. So let's write that. As I was telling you, A goes to C means that the corner A goes to the original position of C. That's what this means. A goes to C. So the A goes down here. The B goes to D. Maybe it's this. Okay, okay. Then B goes to D means that this B goes to the original position of D. So B goes here. This C goes to A means that C goes to the original position of A. And D goes to B means that D goes to the original position of B. All right? So you can see that this is the 180-degree rotation. If you took this guy and you rotated 180 degrees counterclockwise, you'd end up with this. So that's just some notation.
Do you always present the degree measure? Do you sometimes represent it by radian?
Well, yeah, we do.
Okay.
We do. But you can pretty much tell if
Okay.
it's degrees or radians. If there's a pi in it, then you know that it's.
Okay.
It's really better for a mathematician to use radians.
Okay.
I think elsewhere in the book we use radians more, but here, because you're just talking about stuff that you saw in high school, so we just use kind of the high school.
Okay.
Yeah. All right. All right. So this chapter talks about systematic ways of how you would compose symmetries. So we know that this we call this a tableau. That's a way that represents a symmetry. This also represents a symmetry. So how would you find a symmetry that is the composition of those two symmetries? And there's a way to do that. It's just like composition of functions. Again, I'm going to skip over that now because it's covered in the video. Right, but we do need to know how, if you give you one symmetry and a second symmetry, how do you compose those two? And there's a diagram there that shows you how to do that. All right, now, here's an important question. This class is talking about abstract algebra, and one of the important concepts of abstract algebra is the concept of a group. And let's see. A group is a, if you haven't seen, so who here has not seen the idea of group? John, have you heard of that, of what a group is? Mm-hmm. Okay. All right, so I assume you've seen group if you've taken that class. Okay, so I can just mention the properties of group. Group is a set. It has operation. The operation, the set has to be closed under the operation. The operation has to be associative. It has to be identity. And it has to be an inverse. So the upshot of this section is that symmetries do form a group under composition. Your operation is composition, because I can take two symmetries, I can compose them together. So in some ways, symmetry is the most basic type of group. Now, if you do have a set with an operation, then you can make a multiplication table. And these are, in group theory, these are called Cayley tables. So in this section, we talk about Cayley tables and how you compute them. So in the these different symbols represent different symmetries. This table happens to be the symmetries of a triangle. A triangle, if you think about a triangle has the identity rotation, and it has two other rotations, if you think about it, 120 degrees, 240 degrees. And a triangle also has three flips. So the question is, how do those flips and rotations interact with each other? Now, this is a multiplication table. This one says, like for instance, this one says row 1 composed with mu1 equals mu3. And then some of the exercises, I ask you to compute those, and verify those table entries. But you do get a multiplication table, and you can notice in this multiplication table, well, we do have an identity. The identity is the 0 degree rotation. And if you look at this, you can also see that there are inverses for each one of the operations. So for instance, what's the inverse of row 1? Look in the second row and tell me what's the inverse of row 1. So what does an inverse mean? Inverse means it's something that takes you back to the identity. So this one says row 1 composed with the identity is row 1. That's not my identity. Row 1 composed with row 1 is row 2. That's not the identity. Row 1 composed with row 2 is the identity. So row 2 is the inverse of row 1 because it takes you back to the identity. And you can see that, you can also check that it works both ways. Row 2 composed with row 1 is also the identity. So that's how you identify the, let's try again. What's the inverse of mu1? Right here. Right. mu1 is the inverse of mu1. Okay. All right. So I ask you to verify some of those operations. And then, so we have some proofs. So we actually go through the group properties and show that, in fact, symmetries do form a group. And I ask you to prove some of those things. All right, so let's go here. And so here I'm going to slow down a little bit and talk more step by step. Here we have the dihedral groups. Now, what's a dihedral group? I've talked about polygons, regular polygons. You have a triangle, you have a square, you have a regular pentagon, hexagon. For any number of sides, you can have a regular polygon with that number of sides. And those polygons are symmetric. They all have symmetry. So the dihedral groups are the symmetries of these regular polygons. So symmetries of equilateral triangle, square, regular hexagon, or other polygons, heptagon, octagon, nonagon, and so on. So for each one of these, for each type of gon, you have a different dihedral group. So dihedral group just means a group of symmetries of a regular polygon. All right. Okay. All right. So the nth dihedral group is the group of symmetries of the n-sided polygon. So in this case, for instance, I have an 8-sided polygon. All the symmetries of this 8-sided polygon are going to be a dihedral group on 8 sides, or we call it D8. And you'll find that any polygon has rotations and flips, or we call them reflections. For instance, here's a rotation. Here's the starting position of the polygon. How do we get from here to here?
Rotation.
What did you just rotated by how much? Well, full rotation is 360.
Right.
So how much did you rotate it by?
40 degrees.
All right. So is it 40?
Well, no, it's 40 times, it's 180.
No.
Wait, 160.
It's divided, 360 divided by the number of sides.
Okay. Yeah, if you think about it that way.
Okay.
Well, all right, but it's hard to divide by 8, but you can divide 36 by 4. What's 36 by 4?
Or
9, right? So it's 90 divided by 2.
45.
So it's 45. So that's what you did. You took this and you rotated it by 45 degrees. Now that's not the only rotation. You could also rotate it by 90 degrees. Or by 135. So there's several, right? Now here's a reflection. How did you get this one from this one?
It's like a mirror reflection.
Where did you reflect?
From 5 to 1, is it a line?
Oh yeah, you took the line here and you flip it or reflect it. Okay. Is that the only reflection?
Well, I mean, you know, you can move the line from different
Okay.
corresponding.
All right. So here you took the line from 1 to 5 and you flipped it.
Mm-hmm.
You could take the line from 2 to 6,
Mm-hmm.
or 3 to 7, or 4 to 8. And any one of those would give you a different flip. Now, are there any other flips? Those are 4 flips, right? You just think of taking these 2 corners and twirling it around. If I just hold these 2 corners where they are and twirl it around, it's going to move the hexagon back to itself. Are there any other flips?
Are there any other flips from that one to that one? Is that what you're
Well, what I'm saying is, I mentioned that there.
Yeah.
No, forget about this picture. Just think about how many different flips there are of this object. Right? I can flip it. If I hold these 2 corners and flip, I'll get a flip. If I hold these 2 corners and flip, I'll get a flip. If I hold these 2 corners, I'll get a flip. If I hold these 2 corners, I'll get a flip. Are those the only flips? Are there only 4 flips? All right. The answer is no. There's another way. Flip it which way?
All the way backward.
Well, but every time you do flip it, it is flipping backwards.
Yeah.
The question is, what do you flip it around?
Because when you flip it, it's symmetries. You have a
Well, yeah, but we found 4 different ways to flip it with symmetry.
But without the symmetry, can't you just pick it up and flip it all the way up? Without flipping it on one center? Because when you're doing that, it's not rotating around the center.
Well, the question is, you're saying you're picking it up and flipping it,
Yeah,
but the result has to look like the original
okay.
hexagon. Otherwise, it's not symmetry.
Okay.
I mean, it's.
Well, can you cut through the sides instead of the vertices?
All right. So when you say cut through the sides, what do you mean?
Like for example, like points 5 and 6,
Right.
the midpoint, and then
All
you
right.
connect it to the midpoint of 1.
All right. So you're saying, suppose I hold here.
Yes.
I mean, imagine cutting this out of paper. And I hold here, and I hold here, and I flip it. If I flip it, do I get the same thing? I do get the same thing. So you see, it wasn't for just 4.
It's 8.
So it's 8.
I guess will that always be the case?
So that's what you explore in this chapter.
It would have been different if it was kind of shifted on the side and looked like an octagon. It would have been more clear.
Yeah.
But it looks
Yeah.
like a strange
Pointed off.
oblong shape.
Yeah, all right, well, yeah, well, I don't remember if that's intentional or not. Well, the way it's set up is that we put a vertex. If you think about a Cartesian axis,
Yes.
you put a vertex at the 0-degree line. That's how we set it up. That in general, that's a good way to do it. If you draw a polygon, it's good to set your first vertex here at the. If you think about drawing axes, put your first vertex on the x-axis. If you always do it the same way, it helps. All right. So this chapter talks about dihedral groups in general, and it says that no matter what n is, the dihedral group has order 2n. So we just saw the 8-sided. The 8-sided figure, and we decided there were how many rotations? I don't know if we did decide how many rotations. Did we decide how many rotations there are? How many different rotations? Now, we did mention you could rotate at 45 degrees. And there are others, right? 45 degrees is 1/8 of the way around. So I just keep.
8 times.
You know, I can if I rotate by 45 degrees 8 times, I get to 360. Each time I rotate it another notch, I'm getting a new rotation. So there are actually 8 rotations. And then we decided that there were 8 reflections. So that 8 plus 8 is 16. So there are 16 symmetries of the octagon. And then what we do here is, that's true in general. If I have a 20-sided figure, it's going to have 40 symmetries. If I have a 15-sided figure, it's going to have 30 symmetries. Okay, and there's a proof here. And here we're as you can see, we're getting, the nice thing about this topic is there's an interaction between the geometry and the algebra. So you're learning how to represent geometrical ideas using algebraic notation. Now, where you're going with this is that later on we're going to talk about things that you can't represent geometrically, and we're going to use the same notation. And that's the problem with most abstract algebra courses is they don't talk about the geometrical things. They just jump right into the algebra, and you don't know what they're talking about. So it's much better to have a simple example like this, so you know what's going on. All right, so we kind of go into this into detail. For example, let's consider another very interesting fact. We talked about reflections, right? And you mentioned that I can take 2 opposite corners and reflect, or I can take 2 opposite midpoints and reflect. Now, suppose I take these 2 corners and reflect, and then I take the same 2 corners and I reflect again. What happens?
Back to original.
Yeah, so I reflected, and I reflected again, I get the same thing, I get back again to the same original thing. And if you think about it, no matter what reflection I do, that's going to happen. I could reflect around these 2, or I could reflect here, I could reflect anywhere. So in general, if I take the reflection and follow by a reflection, I get the identity. Now, that's what you think by intuition. Can you prove that mathematically? So that's what this chapter goes through, is it talks about how do you show this mathematically, that a reflection followed by a reflection is always itself. Now, that's not true for rotations, right? If I take a rotation, if I take a 45-degree rotation and follow it by another 45-degree rotation, I'm not getting back to the start. I have to go 8 times. Right? So that's true for reflections, but not for rotations.
So when you said rotation, right?
Yes.
So you said for each rotation, so are we increasing the rotation, or is it like making, like doing one rotation and going back? Is that different?
But yes, if I say do the same rotation twice, that's not going forward and back.
Okay.
I mean, technically, going backward, forward is a 45-degree rotation, backward is a 315-degree rotation.
Oh,
if you think about going, if you think about going counterclockwise, you can't count 45. We're thinking counterclockwise.
Okay.
All of our rotations we're thinking counterclockwise. So 45 clockwise is not the same as 45 counterclockwise. All right, so we're using this notation R and S to denote some special symmetries. R in the octagon, R was this basically the smallest possible rotation in Houston symmetry. And we saw that was 45 degrees. Now, let's just think about that. If you have a triangle, what's the smallest possible rotation that gives you symmetry? Let's just write that out. Okay, so I say, so let's hate this. I'll just have to write over here, dihedral groups. Okay. So if I have a triangle, so I'll say this smallest a rotation angle. That gives a symmetry. So what did you say was the smallest rotation angle? That gives you some 120. 120?
I just divided.
Well, yeah, I think that's right. It's 120. And then how about for a square?
90.
That would be 90. And then how about a pentagon? So how are you doing it?
60.
How are you computing it?
360 degrees divided by the number of sides.
360 over 5. Right. That's 72. Okay. And then you have a hexagon. So a hexagon would be 60. That's 360 over 6. Okay. So in general, if I have a whoops, sorry, didn't work. It's not liking me. Okay, so if I have an n-sided polygon, I'm going to have 360 over n. Okay, so I'm going to let R be defined to be equal to the rotation by 360 over n. And then I'm going to let S is going to be defined by the flip that leaves vertex number 1 unchanged.
What do you mean by that?
Well, remember when I talked about flipping, one way to think about flipping is you take 2 points and you flip her
Oh,
flip
so
her on the
it's
top.
gonna leave where
So,
your fingers
so
are.
it's going to leave where your finger is fixed. So when I say S, I'm putting my finger on vertex number 1 and whatever's on the other side. And I'm flipping it. All right, so that's my S. All right. So let me go to some exercises. And I do apologize. This is really kind of a whirlwind tour, and you're going to have to go, probably going to have to go back and watch the videos to kind of fill in the gaps. But I hope you're getting kind of a general concept. I think it's much more organized on the video, and like I said, there's a lot of notes here also that go along with the video. So let me look at what I assigned for 7.4, and I'm going to do some of those. All right, 7.1, 7.2, 7.3, 7.4. So these are the ones I said I would do for 7.4. So let's get this out here. And we'll do here. And I'm going to do the starred ones.
You said you were going to post everything here on OneNote. It's going to be posted on Canvas?
Yes.
Okay.
Well, no, it's going to. I'm going to put the link on Canvas.
Okay, yeah.
And when you click on that link, you will see exactly this page. Yeah. Whoops. Why did it do that? Okay. I don't want that. I want this. I do want to just erase that link there. I don't need that. Okay. But I think I need to make this bigger. Okay. All right. So let's slow down a little bit and let's look at some of these start problems. So the idea of this section is to characterize the symmetries of a polygon. That's the whole idea of what we're doing. So this whole section culminates in a complete characterization of the symmetries of a polygon. So let's look at 2A and see what that
What
is.
are the starred ones?
Starred ones are the ones I'm going to do in class.
Okay, but they still...
Yeah, you
also
still write them up,
feature-
yes.
Cool.
Still write them up, yes.
Awesome.
Thanks for asking that. All right, so let's look at 2, and we can think about this a little bit more. Okay. All right, now, we've been talking about, so 2A is here. Why don't we just grab that and put it on the, well, no, we can talk about it from here. We've been talking about rotations, right? And I mentioned that R, I'm using R to denote the smallest possible rotation. Now, if I follow that by another R, I would call that R composed R. Shorthand way of writing that is R squared. If I compose it with another one that's R composed R, I write that as R cubed. So R to the K is going to be the composition of K rotations by 360 over N. And each time you compose the rotation, you're adding another 360 over N. So R to the K is rotation by K times 360 over N. We also have this convention that R to the 0 is rotation by 0 degrees. And that's your identity. R to the 0 is the identity. All right, now, if RK okay, all right, and you see this more, this is more explicit. So let me snip this. Put that there. Yeah, let me do this. Oh, it doesn't work. All right. Oh, it does work. Okay, so I'll put it here. Okay, and I don't need this. All right, so we have this. And we also have the question, which is this. So this is my first question. All right, so here's my definition. R to the k is rotation by k times 360 over m. And then what I want to do is show that r to the k composed r to the m is equal to r to the m plus k, or k plus m. All right. First of all, does that make sense? What does it say?
Rotate it n times.
Yeah, I'm rotating. You can think of each r as a kind of moving it over a notch. So here I've moved it k notches, and then I moved it m notches. It should be m plus k notches, right? It just makes sense. So how would you write that out? Well, one way to do that, one way to show that is insert some stuff. Okay, so I can say, so to prove this, I can say r to the k is equal to, what that means is that I'm composing r with itself k times. That's what r to the k means. That's how I defined it. That r to the k means I do that rotation k times. And then r to the m is going to be r composing itself m times. Okay? So what about r to the k compose r to the m? It's going to be this, composed, right? And this is k times, and this is m times. Okay. Now, the question is, do I need the parentheses? Can I remove the parentheses?
Yes.
Why? Here's a property of composition that allows me to do that. It begins with an A.
It's associative?
Associative. Okay. Associative property allows you to remove the parentheses. And then this is k plus m times, and this is since composition. See, is associative. Okay, and that's just equal to r to the m plus k by definition.
On homework and exams and stuff,
Yes.
is this enough?
Yes.
Yeah.
Yes, that's enough. But you should, whenever you give a equality or a step, you should give a reason.
Right.
Just give the step, give the reason. Doesn't have to be, you don't have to write out a paragraph. Sometimes you might want to write out in paragraph, or so, but this is also okay. This is okay. Be thinking about the grader, whoever it is, has to be able to follow your argument. So you, whenever you do something, you should say, how can I do that? Why did I do that? What was my reason for doing that? What allows me to do that? All right. All right. So this is a sufficient proof for part A. You could hand this in and get full credit. And see, the key thing here was the associative property. You needed to use that group property in order to make that work. Okay, so let me go to the next starred one that I was going to do, which is 3A, 3ABC. I'm going to do all of them. You guys are spoiled. Okay. So let me copy it. Where is it? 3ABC. Okay. All right, good. Write the reflection S for the pentagon in tableau form. So I mentioned to you, I went over it quickly, but I mentioned to you that tableau form was kind of where you have the two rows, and you have the first, you have the A, B, C, D on the top row, and then you have where it goes on the second row. So I'll do an example here for you what this is. So this one is just 3A. Well, here, why don't I snip this because I'm lazy, and I don't have to rewrite it again. All right. Come on. Okay. Oh, it went over there. Come on back. Come on back. There you go. Good dog. All right. All right. So, so I remind you that the reflection S, when I do my pentagon, the best way to do it is put your vertex 1 over here. The pentagon has 5 sides, so stupid thing. All right. This is going to be a horrible pentagon, especially because it's acting up, but it does have 5 sides. There you go, it has 5 sides. So 1, 2, 3. What I should do is copy a pentagon from the web and paste it, but I've already got this, so okay. All right, now, if I wanted to do S, S is the reflection that leaves 1 fixed. So, as I was saying before, think about grabbing this one. And what else would you have to grab? The midpoint here. And then you twirl it. Okay, that's going to be your S. It's the one that leaves 1 at where 1 is. So let's make the pentagon again here. I can do a better job this time, I think. Oops. Okay. All right, so 1 has to go to 1. Where does 2 go?
Where the 5 was.
2 goes down to where 5 was. Where does 3 go? 3 goes to where 4 was. Where does 4 go?
Where 3 was.
4, and then there's no other choice. All right? So, oh, I did 1, 2, 3, 4, 5. I could do A, B, C, D, E. It doesn't matter, okay? Sorry, I should have done A, B, C, D, E, but I'm too late now. Actually, I think it is better to do 1, 2, 3, 4, 5 because I might do N, and I run out of letters at 32, so, or 26. So, all right. So the question is, what's the second row of this tableau? Where does 1 go to? 1 goes to 1. Where does 2 go to?
5.
2 goes to, as I said, 2 goes to where 5 was. So 1 goes to 1, 2 goes to 5, 3, 4, 4, 3, 5, 2. All right. So this is that's the answer to part A. And it is helpful if you box your answers. Then we know what to grade. All right. So B. How many vertices are fixed by S, and what are they? Fixed means that it doesn't move. So 1 doesn't move. Are there any others that don't move? Everything else moves. Everything else moves. Okay. So I can say only 1, and it's 1. Okay. Now, how about C? What about part C? What is S squared? S followed by S.
Reflect.
Yes, reflect.
Back to where we
Yes,
started.
it's back to where you started. Now you'll see in the book you also can do that diagrammatically because you have 1, 2, 3, 4, 5, and then this is 1, 5, 4, 3, 2. You can do that, and then you're following it by the same thing. 1, 5, 4, 3, 2. So this is S, and then this is S. And if I want to get S composed S, here the S takes 1 to 1, and then this 1 matches up with this 1, and that takes 1 to 1. So S squared is going to take 1 to 1. Now S takes 2 to 5. I match the 5 up here. 5 goes to 2, back to 2, so I get 2 to 2. Then 3, S takes 3 to 4, then I match the 4 up here. It takes 4 back to 3. And you can do the same thing with 4 and 5. Whoops, that wasn't not right. So this is something that you can do both algebraically and geometrically. If you never mind the geometrical picture, if I just wrote down this tableau, you should be able to compute the square. Even you don't have the geometrical picture, right? Because that's how you do it. S squared is S followed by S. So 3 goes to 4, and then 4 goes to 3. So that means in total 3 goes to 3. So we'll be using tableaus a lot in the next chapter. So this is a good way to get familiar with how to use tableaus. Okay, that's 3. All right, what's the next problem? Sorry. Next problem was that I was going to do was 14. I'll skip all the way to 14. Okay. And 14 is and I think it was 14 ABC, right? Okay. All right, so this is going to be a little bit complicated, I think. I may have to punt on this one. Okay. So I think I can give you some indication here. I think when you go back over the previous parts, what I talk about now is going to make more sense. So just take what you can. You know, math in some way is like learning a foreign language. If you go to China to get off the plane, you don't understand what anybody says, but somehow it starts growing on you, and you start understanding it. So even if you don't fully understand, just try to absorb what you can, and then when you go back later, you'll understand it better. All right, now, remember what S is. S is the reflection that leaves vertex 1 fixed. And R is the smallest possible rotation. So there's some proofs before this part in the text. And what we want to prove is that if I take any rotation and follow it by a flip, that's still a flip. It's not obvious, but it's true. If I take any rotation and follow it by a flip, it's still a flip. All right. Then, all right. So let's think about that. Let's look back at some of the results and see if we can prove that based on the results. Now, when it says based on the results, you shouldn't think that you have to start all over again from scratch. You should look back and see what's been proven already and say, well, I can use that, I can use that, I can use that, I can use that. All right, so let's look at the results that we have here. Okay, so all right, let's see. All right, so let me make sure I've got all the propositions. Okay, so first of all, first of all, we know that if we have a n-sided polygon, we're actually going to have n rotations, and here they are. You've got the smallest rotation, then you can do it again, again, and again, again, again. If you do it n-1 times, you're not quite at the end. If you do it n times, you're back to the identity. So you have n rotations if you have an n-sided polygon. All right, so let's see what the next result says. Now, then here we're talking about reflections. All right, now here it says I can take S. Here I can take S, and I can take n. Well, when you say S composed R, what that means is you're rotating first and then you're flipping. So I could take any one of those rotations and then follow it by a flip. Now, it's possible that two of those might give you the same result. Without proving it, you can't tell. Maybe if I rotate 120 degrees and flip it, that's the same as rotating 180 degrees and flipping it. It turns out that's not true. I can prove that each one of these is a different symmetry. So what do I have? So far I have n rotations, and then I have these n symmetries also. I don't know what they are, but I do know I have n symmetries. And the proof, you'll have to go through this to show that. All right. So let me just summarize what we have. So let's see. So the previous results show all right, you know what? I'm not going to be able to finish this, so I think what I'm going to do is I'm going to leave this until next time. So what I'd like you to do is go back and backtrack. Watch the videos that I made, and like I said, I think that once you watch those, what I said today will make a little more sense. You watch those videos. I'll also post this video. If you want to re-watch this video, that will be fine. And then the homework is not due. There's no homework due next week. It's not due until a week from next Tuesday. So you have time to work on the homework. So, but we will be starting in on the next week. I'll be starting in on the next section, which is permutations, which is kind of similar to symmetry. So what you need to do is watch the videos that are already there. Make sure that you're on this canvas. And if we have problems with that, you have to make sure you're on this canvas because that's where all the material will be. We'll just, we'll just go on from there.
Ron, just say you're going to post this?
Yes.
The work that
Yes,
you say?
I'm going to post this video, and I'll also post the link to these notes. Okay. And I'm sorry, it's because the first day was kind of messed up. So, and I don't think everybody got the links to the videos in time. But we'll get there. All right, so I'm going to stop this recording. And if I can, where does it stop? I think it's like, I think I do this.